Welcome back to our ongoing exploration of the OEIS. Today we're diving deep into A000064, a sequence that, might seem pretty simple at first. It's all about making change with coins. Something we all do, right? But trust me, this sequence, it takes us to some really fascinating math.
Yeah, what's really cool about the sequence is that it doesn't just stop at, listing the ways to make change. It actually connects to some really interesting ideas like partitions, combinatorial analysis, and even touches on how complex it can be to find the best solution to this problem.
Exactly. So to make sure everyone's on the same page, A000064, the sequence, it represents how many ways there are to make change for, let's say, cents using the coins we usually use, 1, 2, 5, and 10 cents.
Right. So if you need to make change for just 1 cent, there's only one way to do it, right? You just use a single 1 cent coin. That's why the first number in the sequence is 1. But as you start needing to make change for more cents, the number of ways you can do it, it starts to grow.
And that's where things start getting interesting. We're not just counting things one by one anymore. Now we're stepping into this whole area of combinatorics.
Totally. One of the key things that helps us understand this is actually a comment made by Jor Arndt on the OEIS entry. He points out that this sequence can also be thought of as the number of partitions of n into two kinds of part 1 and 1, kind of parts 2, 5, and 10.
Okay, so let's break that down a bit. For those who might not be familiar, what exactly do we mean by partitions in this context?
Well, think of a partition of a number as splitting it up into smaller whole numbers. So when we say two kinds of part 1, we're just saying that you can use that 1 cent coin twice.
Oh, I see. So it's we have two separate slots for the 1 cent coin, and then just one slot each for the 2, the 5, and the 10 cent coins.
Exactly. And this idea of partitions, it connects directly to a bigger problem that we call the change-making problem. This is a classic problem in both computer science and math.
Now, if I remember correctly, this problem, it goes beyond just coins, right?
Oh, yeah, for sure. It shows up in all sorts of situations.
Yeah.
Think about figuring out the best way to allocate resources, scheduling tasks, or even figuring out the different ways to get a 9-dart finish in darts, The Wikipedia article actually mentions that.
Wow, it's amazing how a problem that seems so simple can have so many different uses. But I also remember reading that this change-making problem can get really tricky from a computing perspective.
Yeah, that's true. It's classified as weakly NP-hard, which basically means that even though we have algorithms to solve it, the time it takes to find the absolute fewest coins possible, it can really blow up as the amount of money we're dealing with increases, even for super powerful computers.
So finding the best solution for really big amounts, that could be a real challenge for computers, huh? Makes sense considering all the different combinations you'd have to go through. But luckily, we have some pretty smart methods to tackle this problem without it taking forever.
Exactly. And one of the most popular methods is called dynamic programming. Have you ever come across that?
Yeah, I've seen it before. The idea is to, break a big, complex problem down into smaller, overlapping problems and then save the solutions to those smaller problems so you don't have to keep recalculating them. It's like building the answer piece by piece.
You got it. In the case of the change-making problem, think of it as creating a table. And this table stores the minimum number of coins you need to make change for each amount, starting from 1 cent and working your way up to whatever amount you're aiming for. There's even a Python code example on Wikipedia that shows exactly how this works. It's really cool if you want to see it in action.
Oh, that's helpful. And it's not just dynamic programming, right? The Wikipedia article also talks about something called the probabilistic convolution tree.
Right, that one gets a bit more complicated. Basically, it's all about combining different coin combinations and using some fancy techniques to make the calculations way faster.
Sounds pretty interesting, especially for people who love algorithms and all those computational tricks.
Definitely. And of course, we can't forget about the good old greedy algorithm. This one's all about always picking the biggest coin that doesn't go over the amount you still need to make change for.
You'd think that would always give you the best solution, right? Using the biggest coins first would always mean using fewer coins overall. But something tells me it's not that simple.
You're right to be a little skeptical there. While the greedy algorithm works great for a lot of coin systems, like the one we use here in the US, it doesn't always guarantee you'll get the most efficient solution.
Yeah, the Wikipedia article brought up an example with old Indian pays denominations, where the greedy algorithm actually doesn't find the best combination.
Exactly. It shows that even problems that seem really simple can have some hidden trickiness to them. And that brings us to the idea of a canonical coin system. That's basically a system where the greedy algorithm does always give you the best solution.
So our U.S. coin system, where picking the biggest coin first always leads to using the fewest coins, that would be considered a canonical system.
You got it. And it's pretty interesting how different coin systems can behave so differently. But for now, let's shift our focus back to the OEIS entry for A000064. There's a lot more to discover there, including the generating function formula, a recurrence relation, and even an asymptotic formula. These things give us even more insights into how the sequence, which might seem simple, actually behaves in some pretty complex and interesting ways. We'll dig into those in the next part of our deep dive.
So you mentioned that the OEIS entry for A000064, it's got this generating function formula, recurrence relation, and even an asymptotic formula. Let's start with the generating function. It's listed as 1 divided by, well, a bunch of stuff. 1 by 2, 1 by 2, 1 by 5, and 1 by 10. I mean, for those of us who might not be super familiar with generating functions, can you kind of break down what this formula actually tells us about the sequence?
Sure thing. Essentially, a generating function is like a way to pack an entire sequence into a single mathematical expression. The powers of x, those correspond to the positions in the sequence, and the coefficients that are attached to those powers, well, those represent the actual terms of the sequence.
So, like, if we were to expand this whole formula out, the coefficients of the xn term, that would give us the nth term of A000064, which is, the number of ways to make change for a set.
You got it. It's like a mathematical blueprint, one that represents the whole sequence in a really compact way. And this specific generating function, it neatly captures those different coin denominations we've been talking about, the 1, 2, 5, and 10. You see them reflected in the exponents of x.
That's pretty elegant. It seems like generating functions are a really powerful tool, especially for people in STEM fields, to understand sequences.
They really are. They create a bridge between the world of sequences and the world of functions, which lets us use all sorts of powerful math tools to analyze and manipulate sequences. That makes them super useful in fields like, computer science and engineering.
And this idea of like building up solutions step by step, we also see that reflected in the recurrence relation listed in the OEI entry. It says AN equals 2 times AN1 minus 2 times AN3 plus AN4 and so on. So what's the big deal about this formula?
Well, this recurrence relation, it gives us a recipe, basically, to calculate any term in the sequence if we know the terms that came before it. If you have a certain number of starting terms, you can use this formula to crank out the rest of the sequence. It captures that pattern of how the number of ways to make change, how that grows as the amount the amount you're trying to make change for as that increases.
So it's like a domino effect where each term is linked to the ones before it.
Exactly. It connects each term to the ones that came before it, showing how the solution builds upon itself.
It's amazing how something as every day as making change can have these really intricate mathematical relationships behind it. And finally, the OEIS entry. It also mentions this asymptotic formula. It says that AIN is like approximately equal to N4 divided by 2400 as N approaches infinity. Can you maybe explain what an asymptotic formula tells us, especially in simpler terms for our listeners who might not be as familiar with the concept?
Of course. An asymptotic formula, it basically describes what happens to a sequence over the long haul. Think of it like a mathematical prediction. In this case, it's telling us that as the amount of money you need to make change for, as that gets bigger and bigger, the number of ways you can combine coins to make that change, well, that grows proportionally to N4.
So even though the sequence is based on, these distinct coin combinations, its growth still follows a predictable pattern as it goes towards infinity.
Exactly. It gives us a sense of the overall trend, looking past the individual coin combinations.
I never would have guessed that making change could have such deep connections to math. It really shows how a problem that seems so simple can lead you to this whole world of mathematical ideas.
It really does. This deep dive into A000064, it's brought us face to face with partitions, generating functions, recurrence relations, asymptotic behavior, and even the computational complexity of this change-making problem. All topics that any STEM enthusiast would find fascinating, I'd say.
And on top of all that, the OEIS entry even hints at a connection to another sequence, A000008, which deals with the number of partitions in general. We started with partitions when exploring the change-making problem, and now we're back to partitions, but in a broader sense.
It definitely suggests there's a deeper relationship between these two concepts that seem kind of separate at first glance. It's like finding a secret passageway that connects different areas of math. Maybe a topic for another deep dive sometime.
Adding it to the list. But for now, let's wrap up our exploration of A000064. What would you say is the key takeaway from this deep dive?
I'd say the key takeaway is that even the most ordinary things, like, digging for change in your pocket, they can have these amazing mathematical depths hidden beneath the surface. This sequence, it may seem simple, but it's a gateway to a whole world of partitions, combinatorics, algorithms, and just the sheer beauty of mathematical patterns. It reminds us that the OEIS is this incredible treasure chest of mathematical insights just waiting to be discovered.
Well said. The OEIS is a true testament to how interconnected math really is, and it's a constant reminder that there's always more to explore. Who knows what other connections and insights are waiting for us in that vast collection of sequences? On that note, we'll leave our listeners with a final thought to ponder. Keep exploring the OEIS. You never know what you might find. Until next time.
Yeah, it's like a reminder that you can find really beautiful math in the most unexpected places. A000064, it might just seem like, oh, a sequence about making change, but as we've seen, it like opens this door to a whole network of interconnected math concepts. It is. It's a perfect example of how the OEIS can be like a jumping off point for like going deeper into things. You start with this sequence that seems pretty straightforward, and boom, suddenly you're digging into partitions, generating functions, and all the challenges of finding those optimal solutions.
Right. And for like a STEM audience specifically, I think those connections to algorithms and like computational complexity, those are super relevant.
Totally. The change-making problem, which we've, talked a lot about today, that's like a fundamental problem in computer science. And it has these like implications for things like making the best use of resources, designing really efficient algorithms, and even understanding the limits of what computers can do.
It really shows how even these seemingly simple problems can have like these huge implications. So for our listeners who are like ready to keep exploring, what would you say is the key takeaway from our deep dive into A000064?
I think the biggest takeaway has got to be just how interconnected math really is. A000064, it's not just about like loose change. It's a gateway to this whole world of partitions, combinatorial analysis, algorithmic thinking, and, just the beauty of mathematical patterns. It really shows the power of abstract thinking and the surprising ways that these ideas that seem totally different can actually be linked together.
Well put. And it really highlights how valuable resources like the OEIS are. They give us this platform to explore and connect these little mathematical gems. So to all our listeners out there, I definitely encourage you, keep exploring the OEIS. You never know what amazing connections and insights you might stumble upon.
Happy exploring.
And that wraps up our deep dive into A000064. Until next time.